Hello! Welcome to Symmtek's video module on understanding thermoplastics and polymer technology. This video is designed to help you become more familiar with thermoplastics and understand the primary products Symmtek works with. In the process of understanding thermoplastics, we will focus on terms such as blends, elastomers, thermosets, amorphous, and crystalline materials. Each of these terms represents a characteristic or behavior of polymer products. So, what is a plastic? A plastic is a polymer. Not all polymers are plastics, but all plastics are polymers. Polymers are made up of many molecules, and these molecules are called monomers. The addition of one monomer to another monomer creates a polymer. A long chain of monomers creates a polymer with a high molecular weight, often much higher than liquids or gases. Plastics begin from a raw material that starts as a gas, such as methane. Through the process of adding heat and pressure to a gas, you create a chemical reaction and convert the gas into a liquid. In the case of methane gas, or CH4, which is 1 carbon and 4 hydrogens, the added heat and pressure changes the structure to 5 carbons and 12 hydrogens, otherwise known as a pentane liquid. If you continue applying heat and pressure, known as polymerizing, the liquid will turn into a solid form. Under these circumstances, methane gas transforms into a polyethylene thermoplastic. The differences in thermoplastics and thermosets help us understand the structure of polymers. Polymers have the capability to have linear structures as well as cross-linked structures. A thermoplastic is a linear polymer that can be melted, solidified, and remelted several times. A cross-linked polymer, or a thermoset, is a polymer material that once melted goes through a process of cross-linking and cannot be melted again. The process of cross-linking is often referred to as curing. Once a thermoset is cured, it can no longer be remelted, whereas thermoplastics can be melted and remelted several times over. The differences between amorphous and crystalline materials are integral in learning how polymers form. When amorphous and crystalline materials are in a molten state, both have the same linear structure. But once the process of cooling and solidification begins, the amorphous material will maintain its linear structure. When a crystalline material begins cooling and solidifying, the linear structure forms crystals, creating entanglement in the polymer. Properties help categorize characteristics such as how strong, weak, or elastic a thermoplastic is. These properties can help define the utility of an amorphous or crystalline polymer. Tensile strength is a property that refers to the amount of force that is required to break a material in tension. Related to tensile strength is a material's tensile modulus, which measures the overall energy needed to break a material when pulled. Amorphous materials tend to have lower tensile strength than a crystalline material. It takes more force to pull and break a polymer with crystals than a polymer that has no crystals with more of a linear structure. Consequently, a polymer with higher tensile strength will have a higher tensile modulus. Ductility is the opposite. A material that has a linear structure with no crystals will have better ductility or elasticity. Elongation, measured in percentage, is the amount of tension a product takes before it forms a permanent set and before it begins to totally break. Elongation is measured in two ways: elongation at yield, or the amount of elasticity measured up to the point the material begins to stretch, and elongation at break, which is the total amount of strain the material can take before breaking apart. By and large, amorphous materials will have more elasticity due to the fact that they have a linear structure and lack crystals. Resistance to creep refers to the amount of energy that is required to completely render a material unusable under the factors of load and time. The higher the resistance to creep, the stronger the product is, which is important when a thermoplastic is used in a structural application of holding a load. Once again, amorphous materials have a lower creep resistance than crystalline materials due to their linear structure. The maximum usage temperature is the highest temperature you can expose a material to without losing its weight or strength. Typically, among thermoplastics, crystalline materials have a greater maximum use temperature than amorphous materials, but there are exceptions to this rule. Chemical resistance is the ability of a material to resist solvents, organic chemicals, and inorganic chemicals without compromising the structure. Because the chemical structure of a crystalline material is more compact, it takes more chemical energy to break the structure of that material than to an amorphous material. Crystalline materials are often desired when an application of a thermoplastic is in the presence of a fluid that contains acids, solvents, or fuels because of the resistance to chemicals. Wear resistance specifies the capability of a material to maintain its weight when abraded or rubbed against a dissimilar or similar material. Wear resistance is influenced by hardness, and crystalline materials often have a higher hardness than amorphous materials, thus garnering crystalline with more wear resistance. Thermoplastics can be formed into a variety of machinable shapes for manufacturing components. If transparency is desired for a product, amorphous materials are the best choice as they have better light transmission. Similarly, amorphous materials are often best for formability using the process of thermoforming. Some crystalline materials are the exception to this, such as polypropylene or high-density polyethylene. Because of their lower chemical resistance, amorphous materials can be bonded using solvents or glues. Crystalline materials, as mentioned previously, are suitable when an application requires wear abrasion or chemical resistance. This may include technical applications such as pumps or gears exposed to a high frequency of abrasion or chemicals. This pyramid categorizes thermoplastics based on their performance and temperature, whether they have an amorphous or crystalline structure. These categories are standard thermoplastics, engineering thermoplastics, advanced engineering thermoplastics, and imidized thermoplastics. Materials higher in the pyramid, such as advanced engineering and imidized, often have stronger properties and performance, but at an increased cost. Examples of standard amorphous materials include polystyrene, ABS, and PVC, while standard crystalline materials include polypropylene and high and low density polyethylene. Engineered amorphous materials encompass polycarbonates, polyphenylene oxide, and acrylics. Materials on the engineered crystalline side contain polyethylene terephthalate, polyoxymethylene, poketone, polyamide, and ultra-high molecular weight polyethylene. Advanced engineering materials that are amorphous are composed of polyether imide, polyphenylsulfone, or polysulfone. In crystalline advanced engineered thermoplastics, you'll find polyether ether ketone, polyphenylene sulfide, and polytetrafluoroethylene, also known as Teflon. At the top of the pyramid are imidized thermoplastics, the strongest of thermoplastics in performance, such as polybenzimidazole, polyimide, and polyamide imide. The usage of these thermoplastics, whether amorphous or crystalline, is predicated on their performance and temperature based on two factors: the HDT, or heat deflection temperature, at which the polymer deforms with a constant load, and the T sub G, or glass transition temperature. The higher the temperature for these two factors, the better the performance. But not all applications require a thermoplastic with the highest temperature. Applications that call for materials in environments that do not exceed 150 degrees Fahrenheit would consider standard thermoplastics suitable. Operations between 150 degrees Fahrenheit and 250 degrees Fahrenheit should consider an engineering thermoplastic. Applications that need to handle 250 degrees Fahrenheit but lower than 450 degrees Fahrenheit would find advanced engineering thermoplastics sufficient. And if performance demands working temperatures above 450 degrees Fahrenheit, imidized thermoplastics are recommended. This concludes Symmtek's Understanding Thermoplastics video module. Stay tuned for our next module focusing on high-performance material, which dives more in-depth into all of the polymer families. We appreciate your attention and thanks for watching our first video module in Symmtek's series of polymer technology.